Okay, good afternoon, everyone. Debating on everything I want to cover today, but I'm definitely going to go over this average atomic mass worksheet with you and do the light presentation that's in 3.3. I don't know if I want to start the electronic structure presentation just yet, but let's just see how it ends up. I do want to point out you'll have your third quiz open today, or not third, it'll be your sixth quiz open today. I'm working on it now. It'll cover 3.1 through 3.3, at least through the light. I probably won't do electronic structure on this quiz. So obviously you want to make sure you're comfortable with the material before you start the quiz. So get the homeworks done as soon as you can. I did open up the next two homeworks, 3.3 and 3.4. So do whatever you can now so future you does less, if that makes sense. So at least get through 3.3 as soon as possible. It's okay to hold off on 3.4 because we'll hit more on that on Monday. I also will point out that we're going to be moving, well, we started already, moving into more theory versus kind of less common sense. So sometimes if you're not putting in the hard work, I guess in the earlier point, you can kind of rely on your common sense to get the right answer. But since we're moving on into theory, I'm just going to keep pushing y'all to continue coming to class because the topics are going to get more and more complicated. So if you don't have someone right in front of you explaining these new concepts, it might be very difficult to learn it on your own. So just keep coming to class, keep chugging along, and ask as many questions as possible because I promise you're not the only one confused. So these are more confusing topics. All right. We finished 3.2's lecture last class. That was on, atomic mass and things about the atom. And we did a little bit about this in the last 10 minutes. We did the M&M exercise at the last 10 minutes. But I really want to go through this entire worksheet with you just because it's very relevant and you might see some similar material in the quiz. So this will be pretty much review, and I might give you some downtime to do a couple of them by yourself, but let's just go through it. If you are online, since you weren't physically here to do the peanut exercise, here are some of your numbers that you can play around with, and you can answer it based on these numbers. If you are in person, use your numbers from last class. All right. We kind of skipped through this first part, but this first part is very important because these would be really good multiple choice questions on an exam. So previously we talked about the subatomic particles of an atom. That was the proton, the neutron, and the electron. So it's one of those three things. Let's just do a review real quick. Your proton is the number that is on the periodic table of elements. It's the same number as your atomic number. So if you look at the periodic table of elements and you find hydrogen, it has a 1 next to it. Not the mass, but the 1 represents the number is in order. That is the amount of protons, and it's also the atomic number. That will never change. No matter what isotope you're dealing with, it's always going to be protons. So this first question says, what subatomic particle are all the same for all isotopes? And I know that wording can be confusing because if you're thinking elements, you might be thinking, okay, what's the same between elements hydrogen to elements oxygen? That's not the question. If I have hydrogen 1, I forget what it's called. Hydrogen 2, it's like deuterium, and then you have tritium for hydrogen 3. Those are 3 different isotopes. But the one thing that is common between all of them is the atomic number and protons will always be the same. So it's about isotopes, not elements. And so this will be protons. It will not change. What subatomic particles are different for all isotopes of an element? The options are going to be electrons, protons, or neutrons. So different from all elements. So if I was looking at hydrogen 1, let me put it up here. It might be easier to visualize. We have hydrogen 1, hydrogen 2, and hydrogen 3. So the number on the bottom is the atomic number and the protons. So notice how they're not changing. The number on top is the mass. But the question, you cannot put mass as the answer here because it's asking about protons, neutrons, or electrons. But what is affecting the weight? I'll tell you now, the answer will never be electrons. They are so small, they cannot affect the weight. So this will either be neutrons or protons. What do you think? Yes, it has to be neutrons. They will change. So remember, if you need to calculate the neutrons, you just take your mass number and you subtract the protons. So 1 minus 1 is 0, so hydrogen 1 will have 0 neutrons. 2 minus 1 means hydrogen 2 will have 1 neutron. 3 minus 1 is 2, so this hydrogen 3 will have 2 neutrons. So you can actually calculate it based on the isotope given. So now that we're more comfortable with those two concepts, let's answer this. Since isotopes have different numbers of blank, they have slightly different masses, which means some of their original physical properties are slightly different as well. Since isotopes have the same number of blank, their chemical properties are the same. So fill in protons or neutrons wherever you think it belongs in the blank. So let's fill it in. Since isotopes have different numbers of what? Neutrons. And then the next one has to be what's left over, and that is protons. So yes, since isotopes have different numbers of neutrons, they have slightly different masses, which means some of their other physical properties are slightly different as well. So remember, physical are things that might be changing, maybe the weight, maybe something else, but chemical properties is completely changing their identity. So if you were to play around with protons, that would be changing the complete chemical identity of it, whereas neutrons might change a physical property such as weight. Is this a question? Okay. Okay, no, it's not. Okay. Let's move on to just finishing this raw data section. If I want to get out of a percentage, just make sure you divide by 100. So you can either move the decimal place over twice, or you just type it in your calculator, divided by 100. So if I do ask for decimal abundance, and I move that decimal place, this would be 0.228 and 0.772. So remember the equation is for an isotope. If I have two isotopes, it'll be the sum of both. This is just a rough, equation, but it's decimal abundance times the isotope mass. So if I'll give you a minute or two to calculate the average atomic mass of this element using this. So remember, you have two isotopes here. So in parentheses, you'll take your abundance times mass plus abundance times mass. And then double check make sure you're typing it in correctly and then calculate your average. Did you already do that? I'll give a minute. If you want to move on to the next conceptual problems. If you're online, I will be asking the answers, so make sure you're doing this. All right, so if you're online, what did you get? This is the average atomic mass where you have to incorporate the isotopes. All right, I'm waiting on an online person to tell me the overall answer, but let's also think about this conceptually. you might have a different number if you're in person, but look at the percent abundance compared to mass. So if this one is majority going to be the peanut M&Ms, I assume, oh yes, I got that too, Fernando. I assume that our answer should be closer to the peanut isotopic mass than the other one. So that's another way to also use your evaluate when you're doing verse, is to say like, what makes most sense? So if percentage wise, it's majority of the 2.5, then I expect the answer to be much closer to that number. So I got 2.09 grams too. So remember that when you set this up, it's a sum. So let's say I had 5 isotopes, it would be the same exact setup, but you just keep adding on the isotopes. Decimal abundance times isotopic mass, decimal abundance times isotopic mass. So it just keeps going depending on how many, which is 2, it's more simple and straightforward. For the next questions, they're more conceptual, and I really enjoy asking these because that just really tests how well your common knowledge is. So these questions aren't meant to be overly hard or difficult. So it says the element consisted entirely of the first isotope. So it's saying that if 100% of this element was dark chocolate, or dark chocolate M&Ms, what would be the element's average atomic mass? So if it was 100% here, what would it be? So it would be whatever mass you have here. Because if you take 1, because if I have 100%, the decimal abundance of that is just equal to 1, right? So that'd be like, if I was to plug it in here, 1 times this number, it would just be the same thing as this number. I don't really have to do any math here because there is 0 peanut M&Ms here affecting the overall mass. It's only dark chocolate, and the isotopic mass is 0.7. And so if it was only dark chocolate and it was 100% dark chocolate, it would be 0.7 or whatever number you had as your isotopic mass. The second question is very similar too. If the element consisted entirely of the peanut M&Ms, so 100% peanut M&Ms, what would be the element's average atomic mass? It would be whatever atomic mass is here. So I can give you the same exact table and ask you the same question, but it would be whatever the isotopic mass is for that specific element if it's 100%. So when I word the question like this, you're assuming it's 100%. Okay. The next one might require a little bit of math, but it says if the element consisted of a 50-50 mixture, so let's say I change the abundance right here to 50% and 50%. What would be the new element's atomic mass? So go ahead and you can type this in your calculator. There are multiple ways you can do this. Some are more efficient than others, but all ways are good. So calculate this for me, and I'll give you a minute. All right. So one of the ways we can do this is coming back to this equation. If you're comfortable setting that up, we're just assuming the percent abundance is now 50. What is a decimal percentage of 50%? 0.5. So one way you can do this, yeah, Fernando, you are correct. So one way you can do this is you can set it up like this, where you take your 0.5 times 0.7 plus 0.5 times 2.5. What is another way you could do this? If I assume that it's a 50-50%, I can kind of take away this equation and just take the average. This is the same exact math as if I just take 0.7 plus 2.5 and divide it by 2. So yeah, it's 2 different ways to do it, but both will give you the right answer if I was to do this. This only works if you have a 50-50. If it's another number that's not so pretty like that, you definitely want to go back to the tried and true equation. For this last one, this one doesn't really require math. I'm just trying to make an assumption here. So math, you'll get the right answer, but I don't want you to do any math. I want you to use logic. So if the element consisted of a 99-to-1 mixture of the first isotope, so it means that 99% of this element is dark chocolate, what would be a good estimate of the element's average atomic mass? So 99% is dark chocolate. What do you think the mass should be? Yes. Yes, you can do the math. You can do this right here, and you can, instead of doing 0.7 and, or sorry, these numbers here, you can do like 0.99 and 0.01. But the goal is for you to make an assumption here. If it's 99% of dark chocolate, that means that that mass should be very, very close to 0.7. Maybe it's 0.701 or 0.71, but it should be pretty much the same number as that. So I'm going to do this little squiggly right here to tell me that it's about or approximately 0.7 grams. So like I can word this question and say if it was 99% of the peanut M&M, same concept. So my goal here is not for you to do the math, even though the math will always be okay. It's to be able to estimate and say, okay, I'm looking here. It's 99%. What does that mean? So can you answer it? That's the goal. So these are really good questions. Remember that I can change this up any way I want for the exam. I can give you new numbers. I can leave things blank, but like, can you answer this? If I was to play around, can you answer this? All right. For this next one, I kind of want to go over it with you for the first one, and then I'll give you some time to go through the rest. So I really enjoy this because this one, once you get comfortable with this concept, it's really quick to do. All you need is your periodic table of elements with you. So I recommend it if you have it at home with you, get it out. If you have it as an app on your computer, so ptable.com, or if you have it on your cell phone, get it out because we need it for these problems. So remember, the number on top is the mass. The number on bottom is the protons or the atomic number. So if I was to give you number of protons or atomic number, that tells you the exact chemical it is, and I can go to the periodic table of elements and figure it out. So can anyone tell me what is number 8 on the periodic table of elements? Yes, it is oxygen. So the symbol I'm going to put here. I'm not going to do O2 here, just leave it as O. If they don't put a number here, I could put a number here to tell you the charge, but right now, since there's no number, I'm going to assume, well, I can also look here and tell you if there's a charge or not. If this number is the same as the number of protons, it is a neutral charge. If your number of electrons is different than your number of protons, it is, okay, so if it's the same as protons, it's neutral. If it's different, it's going to have a charge, plus or minus depending on. But what is not changing is the number of protons. So what is the number of protons? 8. So that's what's on the periodic table of elements. It's always going to be the same thing for oxygen. No matter what isotope of oxygen I give you, it will always have an 8 on the bottom. Based on here, what is the mass? Yes, the top number is the weight of this isotope. So I'll put a mass as 18 here. For the number of neutrons, just know that to calculate the mass, you add protons plus neutrons, not electrons. So protons plus neutrons is mass number. So if you need to go backwards, you take mass number and you subtract your protons, which gives you what number? 10. Okay. Now this number also it never changes. It will always be the same number as the number of protons. Okay. So I'll give you a few minutes to do the rest of it. Kind of use these numbers to go backwards. Okay. If I give you an atomic number or a proton, just know it's the same number it's on the periodic table of elements, and that's where I would start.
got the positive and negative charge, so we can put that.
You can put that here in the top right. Let's, I guess, start going through it a little bit. These are a lot of fun to me. I'm also very biased, I understand, but these are like solving a puzzle going backwards. The way that my mind would always start is never at the number of electrons. It's always if they tell me protons or atomic number. That's the first thing I look at. And they told me the atomic number was 8. So that means that the element involved is going to be oxygen, always. This number will never change. I'll put an O here for oxygen. I have my identity based on my atomic number. Since these are always going to be the same number, I'm going to go ahead and put an 8 right here. Okay. How many number of neutrons? Anyone tell me? Remember, to answer your mass, you take protons, oh, I'm sorry, I'm looking at the wrong screen. Protons plus neutrons. So if I have my mass number, I just take mass number minus 8 are protons, and that gives you neutrons. So this one should be 9. Am I right? I'm like, I don't trust my basic math, which is embarrassing. It also wants us to fill in here, okay? So the mass number goes on top, and then the atomic number or the number of protons go on the bottom. But look at the electrons. Electrons are negatively charged. So if it's neutral, if it's a neutral charge like this top one, these numbers would be the same number. Because I have 2 extra electrons here and they're negatively charged, what charge do you think this oxygen atom has? Yes. So if I have too many electrons, that means I'm going too beyond the neutral. That means it's negative because they're negatively charged. So this would be a 2 minus. So I'll put a 2 minus in the top corner. And just remember that. So same number here, it's neutral. Different number here, we have to collect the charge. If this number is smaller, it'll be a positively charged. If it's bigger, it'll be a negative. Okay. What element is number 12? Magnesium, so that's Mg. All right. So protons and atomic number are always the same. So I'll put a 12 here. What's the mass? So yes, protons plus neutrons gives you mass number 25. Okay, let's fill in this over here. What number am I putting on top? The mass number. And what about the bottom? 12. All right, let's look at the electrons. If this was a neutral where I can leave this blank, these would be the same. But now I have 2 less electrons. So what is the charge? Yes, so electrons are negatively charged. If I lose those 2, I now have a positive charge, and it's a 2 plus. Okay. All right, this one's also a 12. So I'll put a 12 here. That means that it has to be magnesium too. All right, what's the mass number? So 12 plus 14, so remember protons plus neutrons is going to be 26. So what am I putting over here? Yes. And then what about, yes, this isn't always, Fernando. Atomic number and protons are always the same, and they're always the number that they are on the periodic table of elements in order. So hydrogen 1, helium 2. That tells you the number of protons and the atomic number. It's an always. Everything else can change, but protons and atomic number always stay the same. All right, so this is neutral, right? Because these numbers match, number of electrons to number of protons. So this would be, I could put a 0 right here if I want, or you can leave it blank. Just depends on what you want to do. All right, last one. What's number 11? Sodium. Which means that the atomic number here has to be the same as the number of protons. And then what's the mass? So 11 plus 13 is 24. So 24, 11, and then what charge? It's going to be a positive 1 because I've lost an electron. If this was a neutral, it would be 11 and 11, but losing a negative 1 charge now gives me a positive 1. All right. So I like this type of table. You know, get comfortable, practice it. There is some questions in your book that has practice. If you want to practice using our homework, I would definitely practice that. But this is a very fun activity, and the more comfortable you get with this, the faster you get. So right now, we might be going a little slow, but when we get comfortable with these concepts, this could be done in like under a minute. We're going to compare and contrast the mass number and the atomic mass. So mass number is dependent to the isotope, where the average atomic mass is where I have to take into consideration all of the isotopes available and their percent abundance. So mass number is, I guess I don't have the definition in front of me per se, but what I would say it is the mass number is the mass of individual isotope, and then combined so this is not perfect, but I'm like kind of like give myself keywords so I can help remember this. So I'm combining all of the isotopes with their own mass numbers and their percent abundance. It does affect the average atomic mass. So mass number, does it describe an element or a single isotope? Yes. So the mass number goes to an isotope where the average atomic mass is for an element. Okay. Is mass number shown on the periodic table of elements? No, look at hydrogen on your periodic table. Hydrogen only shows you one thing, but there are 3 isotopes of hydrogen, and the masses of those isotopes are not shown at all on the periodic table of elements. So no, yes, the average is shown. Is it a whole number or does it have decimal places? So if you look at the periodic table of elements, are there decimal places? Almost for every single one. I'd say the only ones that don't are the higher ones that are kind of newly discovered. So the mass number will always be a whole number. Because remember, it's an isotope where you add the neutrons and protons and we don't split them. We're not splitting such subatomic particles, so they're always going to be a whole number. But the reason why we always have decimal places on the periodic table is because we're incorporating a calculation to figure out the average. All right, let's, keep talking. Indium, atomic number 49, has 2 naturally occurring isotopes, indium 113 and 115. Sometimes we will write it like this because if we know the atomic number, the number on the bottom never changes. So if we're focusing just on mass number, we'll leave the atomic number out. Which isotope has the greater natural abundance? Why? Let's look at the periodic table of elements. What is the number for the mass on the periodic table of elements? Can anyone see it? 82? Is that number closer to 113 or 115? Yes. So which isotope has the greater natural abundance? Is indium 115 because the average is closer to 115? I love this question because I'm not asking you to calculate anything. I'm just asking you to kind of look at the periodic table and use kind of like an assumption. Hydrogen has 3 naturally occurring isotopes, 1, 2, and 3. Those are the masses. What can you infer about the natural abundances of these 3 isotopes? So first, let's look at the periodic table of elements. I think the number for hydrogen is 1.008. So this question is quite vague, but it's asking about the abundance. So let's say I was looking at like 1H, what do you think? So 1H versus 2 versus 3, which one is the most abundant? Do you think out of 2 or 3, which one is more abundant based on this number? Probably 2, I agree. So I would say both of these numbers would be very, very low, but I do think 2 would probably be higher than 3 just because of how low this number is. I would probably say 1H is greater than 2H, which is greater than 3H. So yeah, this is not like an all right question. This is just way like, can we look at a number and kind of make some assumptions? So I like this types of questions. These would be really good questions for maybe the short answer portion on our next exam, because I really want to challenge how comfortable you are with this. And I know this might be a little overwhelming, but practice is really what makes the difference. I know with myself, when I first learned isotopes, I just nothing stuck. I'll tell you now, nothing stuck until I had to come and teach. And I was very, very, very insecure about my ability to teach it. But it comes the more you do it. And so I would just sit in my office and just do homework. I would do my students' homework and I would make more homework problems. So what I did before coming in today was I opened the back of the book and I practiced a bunch. So as we're learning, I do highly recommend, I would say for the next 15 minutes, why don't we open up our homeworks and do some of those homework problems? And then I'll be here if you have any questions, because I kind of want to do light. I kind of want to just hold off on electron structure and do that next class, just because I don't feel like teaching that right now. I'll rather just talk about light. So we'll do light for the next half, but let's just do our homework right now. Pause the recording.
Recording in progress.
All right, so hopefully you got a good chunk of your homework done and it makes more sense to you. If you have any questions on homework, of course, we still have time after lecture or during my office hours, we can go over those problems. Let's move on to light. We're gonna kind of continue connecting the dots. We talked about the atom, and we're now gonna relate that to light. So our objectives from this are to recognize light both as a wave and as a particle. It can exist as both. To acknowledge light as a probe, which gives information about the particle level nature of matter. To calculate the wavelength, frequency, and energy of light. And to characterize the relationships between wavelength, frequency, and energy as either directly or inversely proportional. So this concept will have a little bit of math in it, but we will also have some logic questions where we can still kind of talk about our expectations and does it make sense. So let's go to the beginning, the interaction between light and matter. So we already kind of have an understanding about light because we think about sunlight and how, we interpret that coming and hitting our planet. So the way light interacts with matter in the lab, which is macroscopic, what do we see? Tells us a lot about the particle level structure of matter, microscale. So an example would be, do you see color? So, if you see a different color, that's how light is interacting with matter. So are you seeing, if you look at a mirror or if you have something that light bounces off of, like a shiny car, so you kind of already have an understanding about like reflection, refraction, things like that. What we're doing in this section is we're taking our macroscopic knowledge of light and talking about it microscopically or at the particle level. In the lab, if you're taking engineering with me, you'll definitely have a light lab. If you're taking Gen Chem 1 and Gen Chem 2, you will also have a light lab. So typically in lab, we'll have an instrument that can read things, where you'll have like a lamp that represents sunlight, or if you have like a xenon lamp or something like that, it irradiates a sample. And then you have a detector on the other end that can either detect how much of the sample is being irradiated, how much absorbance the sample is, reflection, things like that. So different instruments can measure different things. But typically the way we measure is we take a light bulb, a special light bulb, not just any light bulb, shine it on a sample and measure something. So wave particle duality, sometimes we kind of get confused. Light can act as both a particle and a wave. And I know it might seem that they are very, very different, but it kind of acts as both. So it's just one of the big ideas from quantum mechanics. And many things that we think of as being particles also have properties of waves and vice versa. So it can be both. It doesn't have to be one or the other. So we can have light act as a wave, but also as a particle when it's going to, move through space and hit something. So light as a particle. So these are just the main things we're going to hit on as light as a particle. So we talked about representative particles when we were doing the mole conversions, where we talked about formula units versus molecules versus ions. This is similar. So particle is going to be this kind of similar to like atom or element. So when I'm saying light as a particle, I kind of want you to think of it like light as an atom. It's not the same, but that's what I mean when I'm saying particle. It's like a small, very tiny thing is coming from space and hitting a piece of matter. So we call it a photon. It's just a particle of light. We can measure the energy because light is energy, heat. So we can do energy by adding heat or removing heat, but also light can also add energy. So if you want to talk about solar cells, to make solar cells work, you have to add some type of energy source. In that case, sunlight. So sunlight can be used as an energy source to create electricity in these solar cells. So photons with light, that is going to require energy, or it's going to have energy come off of it. The photoelectric effect means that electrons are emitted from material, most likely going to metal, to have light shine off of it. So if you ever were to like see a shiny car, that's the photoelectric effect. So having that light bounce off of it. The photovoltaic cells, that's just me going back to solar cells. That's my expertise, and I love solar cells. It's when it converts sunlight into electricity. So solar cells have come a long way. I don't really recommend putting it on your house just yet, just because you have to be in your house for a very long time to pay them off. And the contracts are, I'm just going into something. When I bought a house, they are predatory. I don't know if anyone has a house. Predatory with how many times they knock on your door trying to sell solar cells. Solar, it's great. It really is great, but their contracts are predatory because they have it in fine line that says like you can sell your house, but the contract is still yours. It's still on you to pay off your solar cells, solar panels. So if you have, sorry, I'm like going on a rant. So you don't want to buy solar panels unless you know you could pay it off all at once or very quickly, or you're staying in your house for a very long time. But I am a big fan. I'm just like, I'm not in my forever house, and so I'm always trying to tell these predators like go away because they keep trying to sell me solar panels. But yeah, solar cells are awesome. I think using sunlight, I'll tell you now, out of all of the renewable energy, solar is the best option because wind is awesome. We're never going to get rid of wind, but those turbines can hurt bird population. We can use tides and the way our currents and water to also create more renewable energy, but it can hurt ecosystems down there. Creating dams, it's awesome because you're going to have that water flow, but you're hurting ecosystems. So there's always going to be a plus and minus, but sunlight doesn't hurt. And we live in Texas, so we have an abundance of sunlight. So I think solar is biased. Solar is the best option, safest option, and most abundant option. So, light also acts as a wave. Sorry. So as a particle, it does bounce off matter, but it can also act as a wave as it's traveling through space as that wave. It can hit something and be refracted. It could be reflected. It can be diffracted. And light happens at different lengths. So we have the visible spectrum, which I'll get into in a little bit, but different lengths tell you the colors of what's going on. This right here is a prism. So prisms are a lot of fun if you have kids or if you were a kid. I mean, we all were kids, but when you were a kid, we got to play with prisms a lot, where you take this piece of glass, you hold it up to light, and it splits that light particle into as a wave. It splits it into all of the colors of the visible spectrum. So light can act as a wave using these. So our relevancy is going to be wavelength and frequency. So how often is that wave hitting in a specific amount of time, and the length of that wave. So what the most common thing we think about when we think light are going to be the colors. This is the visible spectrum. And I'll tell you now, this is a tiny, tiny little blip on the full scale of wavelengths. Wavelengths, when you think about gamma rays, X-rays, IR spectrum, that's a massive spectrum. And we see this little tiny blip, that's just going to be the colors of visible light. So here is just the visible spectrum with those wavelengths. I want to point out that energy is growing as wavelength is decreasing. Y'all see that? So if I wanted to compare energy, and we use a lambda for wavelength, I believe it's lambda, pretty sure. If energy goes up, sorry, that was a terrible. Energy goes up, wavelength goes down. So are they proportional or inversely proportional? Inversely, so that would be E. And it's very important because if I was to like ask you a logic question on the exam that says, I'm comparing red light to blue light, which one has the most energy? There's no math required for that. So blue light will have lower wavelengths, and so that will be more energy. It's like, that's a great way for me to ask that question. About comparing energy versus wavelength. So the smaller the wavelength, the more energy that it's giving or requiring. Yeah. So red, which is longer wavelength with less energy, is going to be between like 650 to 700. Orange will be between like 570 or 580 to 650. Yellow is tiny. It's a little bit in here. Green's more broad here. Blue has a bunch of different colors in there. If you want to like blue versus indigo, it's all blue. And then purple will be kind of, violet will be towards the end. So it really just depends on where it's going to land, but this is the whole visible spectrum. So here's what I meant by the wavelength spectrum is vast. So gamma rays all the way over here to TV or radio waves to the left. So let's look at this. Energy is growing the way that they wrote it. So which means that wavelength over here is going here. So as energy increases, the wavelength gets shorter, and as energy decreases, the wavelength gets bigger. So here's another way I can ask a question. I have A, B, C, D. Which one requires the most energy? Yeah. So I gave you this picture. You can make the assumption since energy is going one way, the wavelength has to go the opposite because they're inversely proportional. So I can ask you a question that's like that, saying like which one has the most energy or which one has the least energy? And visible light smack dab in the middle. But that's just a concept that we can just continue getting comfortable with so we can use deductions to answer those questions. Is inversely proportional to wavelength. Okay. Any questions so far? Okay. These are more theory based. I know that a lot of these unit 3 stuff is a very heavy in theory, but if you want to see how we would ask questions is looking at the homework or practice exam or even the quizzes. So I'm not going to be testing you on like, do you know what year Dalton's model came out? I'm just going to be talking about theory. Let's move on. So wavelength and frequency. So wavelength is that lowercase lambda. It's distance from peak to peak. So different wavelengths will vary depending on what you're analyzing. So if I'm looking at red versus blue, the wavelength will get bigger or shorter. Typically wavelengths, the most common units are going to be nanometers if we're discussing visible light, but you can also see it in meters, centimeters, or anything in between. So it's a distance. So it's going to be a unit of distance. And then frequency is how much you're going to have the wave happen in 1 second. So we use hertz, but also hertz is in seconds to the -1. I want to just point this out because this is the first time I'm seeing a unit with a negative sign. We talked about, I think I talked about cubic centimeters before, or cc's if you work in the medical field. So cc is cubic centimeters, and that's the same thing as me writing a cubic centimeter. That's the same thing as one milliliter. This is the first time I'm seeing a negative exponent. So that negative, like if I was to have a positive exponent, it just means it's in the numerator. But if you have a negative exponent, that just means this is the same thing as 1 over s. If I had 1 over s squared, that would be equal to s to the -2 and vice versa. But since it's just s in the bottom, that's why it's to the -1. So you can write it either or as 1 over s or s to the -1. But hertz is typically going to be given in hc or s to the -1. So the more, I would say the more energy required, more frequency. And I'll show you how I know that. Let's keep connecting the dots. Here's a really helpful equation to connect the speed of light, because that, we have to incorporate the speed of light when we're talking about light going from the sun to hit the earth. The speed of light is important. So c is the speed of light. It is 3 times 10 to the 8th. And once again, if I write it like this, meters to the second -1, that is the same thing as me writing meters divided by seconds, so meters per second. So if you see it like that, don't worry. If it's to that negative exponent, it just goes in the denominator. All right, let's talk about the relationship between lambda and frequency. So wavelength and frequency. If I was to like rearrange this equation to focus on lambda or wavelength, I would have to divide by it on, or divide by the other thing on both sides. So C divided by B. And then if I was to look at frequency, that's C divided by lambda. The reason why I did that is I want you to kind of answer or think about comparing them. As one goes up, what does the other one do? So based on the equation here, you have lambda in the numerator. So if I was to put this over 1, me saying it's in the numerator, and I have frequency in the denominator on the other side. Is it proportional or inversely proportional? Yes, because one's in the numerator and one is in the denominator. They are inversely proportional. Which means as your wavelength gets bigger, your frequency gets smaller, which makes sense when you think about going back to that previous slide. As your wavelength gets bigger, that means there's going to be less cycles per second. That's why it's getting smaller. As your wavelength gets smaller, you're going to have more cycles per second. So they're inversely proportional. And that's how I can make that assumption. So as lambda goes up, frequency goes down. As lambda goes down, frequency goes up. So they're inversely proportional and are opposites. If we need to solve using verse with this type of equation, I can remember, okay, if it's doing this, it should do this, so I can help and fix if I was to make a math error. Here is another equation, is we're now going to connect energy and those waves. So there are two equations here because I can focus on just wavelength or frequency. The way they wrote it was E, energy, which the unit is typically joules, is equal to Planck's constant, which is this number right here. Planck's constant times frequency, or since frequency equals C divided by lambda, they just took this and threw it there. Because I'll tell you now, sometimes you're given frequency and sometimes you're given wavelength. And you don't need to have both to answer the problem, you just need one. So energy equals Planck's constant times frequency, or Planck's constant times speed of light divided by lambda. Okay. See the way that this unit is written, joule seconds, you can also write that as joules times seconds. They don't have it seconds to the -1, so it's all in the numerator. Okay, let's compare. Let's focus on E equals HV. Energy to frequency. Are they proportional or inversely proportional? Because frequency is in the numerator and energy is in the numerator, they are proportional. I always forget to say that word weird. So as E goes up, so as energy goes up, frequency goes up, which makes sense. More frequency, more energy. Less frequency, less energy. Kind of going back to atom collisions. More collisions, more energy. So it goes down, frequency goes down. All right. Now let's look at energy versus the other equation. So energy versus lambda, so wavelength. Are they inversely proportional or proportional? So lambda's in the denominator, so they are opposite. As one goes up, the other goes down. So it's kind of the same concept. Since these are proportional, it's going to match. It's going to be matched and be inversely proportional to the lambda or the wavelength. Okay. And if we understand that concept, we can answer these problems or check those mistakes. So it's really important to kind of be able to determine how is it proportional or inversely proportional based on those equations. We're almost done with light, I promise. All right, let's review verse. As you get more and more comfortable with problem solving, remember that I can provide any type of equation for you and you can still apply verse to it. So it's a problem solving approach for word problems. V for variables, E for equation, R for rearrange, S for substitute and solve, and E for evaluate. I always will highly recommend doing this process because if you do have a short answer portion of the exam, this is what we're looking for, even when you go beyond 1320. You need to be able to write it all out to make it obvious to the person who's grading what's going on. If you were to just throw numbers in there, I would not know what's going on. So you want to include your units. You want to make it obvious what's going on. And this is how we do so. So example 1, when you get these types of problems, read the question twice because you might miss what the question is asking. Find the frequency and the energy. So it's asking for two things. Of the helium neon laser, which has a wavelength of 632.8 nanometers. So let's do a part 1 here. Let's find frequency. If I don't know my energy, I can't use the frequency equation of E equals HV because I don't have energy. I can't have two unknowns in here. It wouldn't work. So I have to use the other equation, C equals, it was frequency times wavelength. I have to use the other equation. If I give you an equation sheet, do you know when to use the certain equations, when is the right time to use them, and how? So V, variable, C equals speed of light, which is 3 times 10 to the 8 meters per second. V we do not know. And lambda is equal to 632.8 nanometers. So E, equation, we just found the equation. V we did. R, rearrange. So if I wanted to rearrange this equation to solve for frequency, I will divide lambda on both sides. And my frequency equals C divided by lambda. Okay. Substitute and solve. Sorry, dropped my pen. Look at the units. So look at the units of C and look at the units of lambda. Are they the same? Meters and nanometers are not the same. Majority of the time with these questions, you're going to be given something in nanometers and you have to convert it to meters because speed of light is in meters. If you do this problem with the wrong units, you'll end up with the wrong answer. So if I want to remember, does anyone remember how many nanometers are in 1 meter? This is a review, okay. So if I have 1 meter and I go, nanometers are very small, so I go to milli, or I can go to centi, that's 100 centimeters in a meter. Milli, 1,000 millimeters in a meter. Next would be micro, that would be 1,000,000 micrometers in a meter. Next would be nano, 1 billion nanometers in 1 meter. So 1 meter equals 1 times 10 to the 9th nanometers. Okay, so we have to substitute here and get those units correct. And you can move the decimal place over 9 times, or you can type in your calculator. Just make sure you type it in correctly, 1E9. And once you have all of your substitutions, you can solve. Let me get a different color. Frequency and wavelength are inversely proportional. Also, if I take a very, very big number and divide it by a very, very small number, I should be getting an even bigger number, much bigger number. But yeah. So when I type this in my calculator, or you can type it in, what do you get as your answer? Okay, I'll give you a moment.
That's 4.74 times.
Yes. Let me just show you the cancellation of the units. So I have meters here and I have meters here, and my seconds is still in the denominator. So my answer is 4.74 times 10 to the 14th. It's a big number. And you could write that as seconds to the -1 or 1/2. It still has to be in the denominator. That's hertz. That's okay if you don't have that memorized. Just seconds to the -1.
That can also be written in first.
So just a reminder for these problems, majority of the time you have to convert the wavelength to the correct units. I can give it to you in centimeters, I can give it to you in nanometers, but because C is always in meters per second, you have to make sure your units are consistent. So double check that before you solve. Meters, I would just do everything to meters. I mean, if you want to be extra, you can also convert speed of light from meters to nanometers, but I wouldn't recommend it. Okay. We still didn't finish the question. So if you do practice these problems, make sure that you, before you move on to the next problem, you double check. So it's asking for frequency and energy. So we have frequency. Let me just write down my variables for verse. C equals 3 times 10 to the negative, no, it's positive 8 meters per second. I know my wavelength, and I'm just going to write it in meters because we already did the math. Um, 6, 30. Frequency, I'll just rewrite what we had on the last slide. Okay. For energy, there were two equations. It doesn't matter which equation you use, because if you notice, for this equation, I just need frequency, and for this equation, I just need C and wavelength. It doesn't matter. It doesn't. So I'm going to do one example with one equation. I'll do the next example with a different equation. You just need to do what's easiest for you. For instance, if you forgot how to solve for frequency and like you blanked here, just use the other method. You know, like you can kind of pick and choose what you're most comfortable with. But let's do HV for this one. So V, we have our variables. E, we have our equation. R, rearrange, don't need to. S, substitute and solve. We don't need to substitute, everything is good. Okay. Double check your units. The seconds will cancel. Let me get a different color for that. And this is why it's so very important to always write your units when you do your math, because if you ever confuse what your overall answer units are, this is how you can decide. I don't need to remember that it's always joules, because at least I know, okay, they cancel out and I'm left with joules. So E equals, I got a big, or no, a small number, 3.194 times 10 to the minus 19 joules. Okay. So double check my math. Make sure that you're typing this in as a negative 34, not a positive 34. So it should be a very small number. And that is the energy for one photon. That's why it's such a small number. If I had a mole of photons, that energy would be a very different number, but this is one individual light particle. I'm going to let y'all do the next one. It's very similar. Find the frequency and the energy of the blue-green argon ion laser, and it gives you a wavelength of 488. Okay? So y'all find the frequency and energy using the same process from the previous slides. So I'll give you about 2-3 minutes, and we'll come back and analyze. Do both that and energy? Or just frequency? Do both, okay. So the setup is the same exact as before, you're just changing out the lambda for the new number. This lambda is a lower wavelength, which means our frequency should be higher and our energy should be higher than the last one, from 600 nanometers to 400 nanometers. So my frequency I got for this one was 6.15 times 10 to the 14th, 1 over seconds, or seconds to the minus 1. So very similar, yeah. The next step would be to calculate energy. For that one, I'm going to use the different equation. I'm going to use energy equals hc divided by lambda, where h equals 6.626 times 10 to the minus 34 joules second. E equals 3 times 10 to the 8th meters per second. And then lambda was 4.88 times 10 to the minus 7 meters. So E equals 6.626 times 10 to the minus 34 joules seconds, 3 times 10 to the 8th meters per second, 4.88 times 10 to the minus 7 meters. So what units will I have? The seconds will cancel and the meters will cancel. So I'll be left with joules. I got 4.07 times 10 to the 19th. These are so bad. As long as you have those equations in front of you, no matter what wavelength I give you, I can give you a very big number. It doesn't matter. You can still answer it based off of what random numbers I'm going to give you, but this is not changing. Like the scheme of this is not going to change. So continue using verse to try to help you answer these problems. It's 1:29 right now, and I'm done with these slides, which means we have an additional 10 minutes. If you need to go, no worries. If you want to take the next 10 minutes and maybe continue working on homework while I'm in the room with you, you can ask me questions if there are any questions on homework or any of the hard questions on homework I can help with. But yeah, I'll stop the recording, but I will still be here for the next 10 minutes.